Okay, here we go. This is Unit 1, all the extra material that you need to know if you're taking physics for honors. I would encourage you as I go through here to pause the video and make some notes or work through some of the problems, or you can just see me work them out, but sometimes some of the more difficult problems you might want to stop, work them out, and then see if you get the same answer as I do. There are practice problems for all of these that you can go through in your packet. Okay. So some extra things you need to know. First thing is you need to always make sure that you're following rules of sig figs. Just a few basic rules of sig figs. Here's some of them. All non-zero digits, and hopefully you know some of this already, and any zeros contained between non-zeros are significant. So remember, significant figures are they are anything that is a measured digit. So if I have the number 257, of course there are three significant figures in that. But if I have the number 503, even though this is a non-zero, no, it's a zero between non-zero numbers, this also has three significant figures. Leading zeros don't count if you don't have any numbers before that. So you could have a number like 0.001, and that only has one significant figure because these are basically just placeholders. However, if you are to write a number after those digits that are zeros, you have now created values, or you have measured those values. So this one actually has three because trailing zeros do count as significant figures. These are placeholders. This is obviously significant, and these are significant as well. Otherwise, we just wouldn't write them. And then trailing zeros may or may not count as significant figures, meaning if I have the number 100, that is not significant. Actually, these zeros are not significant. It only has one sig fig. But if I know I measured the tens in ones place, then I would put a decimal point, and then all of them would be significant. I'm just going to really quick review multiplying and dividing and adding and subtracting. Like, for example, if we're doing a bridge, like 23 years, and then I build this big long bridge and I'm converting it to seconds. Oops. This has two sig figs. We're multiplying across it, the top, and dividing them by what's in the bottom. You're always going to go back to that original digit. So just real quick, when you're multiplying and dividing, and you multiply two numbers, like 52 times 105, whichever of these numbers has less sig figs, this has two, this has three, your final answer is only allowed to have two sig figs. That's fun. When you're adding and subtracting, there's different rules. Adding and subtracting. The rules for adding and subtracting are as follows. So, for example, if I add the numbers 21.3 plus 14.72 plus 28. If I add those in my calculator, I get the number 64.02, but I'm not allowed to be that specific because I am only allowed to be as specific as the least specific number. So this one goes one place past the decimal, this goes two places past the decimal, but this one has 0 places past the decimal. Right here, there's nothing past the decimal point, so I'm not allowed to include either one of the digits past the decimal point. So you're only allowed to give the answer 64. That's for adding and subtracting, different rules for multiplying and dividing. Okay, on to the next one. What you need to know is, like for regular physics, they have to know giga through nano. You have to know that too. But we have these additional 3 on the top and 3 on the bottom that you need to be able to use and work through. So I'll just work through one of them and then I'll give you the answer for the other one. So for example, we're going from petameters to femtometers. So again, you should be able to go to farther metric prefixes. So 453.4. And remember, there's a difference between the capital M and the lowercase m, so make sure you're distinct. The way that I taught you before, capital PM, petameters go through the base unit first and then go from the base unit to the other prefix. the one that's higher up on the list. So we look over here, PETA is higher up on the list than the base unit. Remember, the base unit's right here. So PETA gets a 1, and then PETA means 10 to the 15th. And then over here we have the base unit higher on the list. Femto means 10 to the negative 15th. But remember, we don't count the negatives. So we multiply across the top, divide by what's in the bottom, 453.4 times 10 to the 30th. We add the exponents when we're multiplying. However, that's not in proper scientific notation, so we move our decimal over 2 places. 4.53, 4 times 10 to the, remember, we make this 2 places smaller. We make our exponent 2 places bigger. Then I go back, cancel my units out, and I'm left with femtometers, and there's my answer. You can go ahead and take a second, pause the video, and try example number 2. Once you finish that, you can check your answer, which is 9.3 times 10 to the 18th. I'm not going to write out the bridge for this one. You go ahead and try it. See if you can get that. It's pico. Remember, there's a lowercase p to atto. So we're going from pico to atto on that one. Grams. Okay. The next one, for honors, you need to be able to convert with cubed and squared values for our prefixes, or excuse me, with our conversion factors. So instead of just centimeters to kilometers, we're going centimeters squared to kilometers squared, or inches cubed to centimeters cubed. So let's go ahead and do something like this. 20.0 centimeters squared. It's basically the same outline. So because I'm going from one prefix to another, I'm going to go through the base unit. The base unit is meter, but of course it's meters squared in this particular case. And I'll just set it up the same way. Meters squared to kilometers squared. All right, so I use the same method. I look at my metric prefixes, which one's higher on the list. Well, the base unit is higher on the list, so it gets a 1 with it. Centi means 10 to the second. However, if you're squaring the unit, you have to square the conversion factor as well. So it's not just the same as when you have meters and centimeters. Since you are squaring the base unit, you have to square the conversion factor. Kilometer is 1. Kilometer means 10 to the third, but of course then I'm squaring it again. Squaring the 1, squaring the 10 to the third. So it's a little bit different. So then we get 20.0, keeping our sig figs. That has 3 sig figs. We need to keep them the whole way through. Times, well, basically not times, all over. Remember, when you take a power to another power, you multiply those exponents. So we have, this is the same as 10 to the 4th. This is the same as 10 to the 6th. And then on the bottom, I would have 10 to the 10th. But we don't want to leave it like that, so we put it as 20.0 times 10 to the negative 10th, but again, not in proper scientific notation. So 2.00, both zeros get kept because they're both significant. So we made it 1 place smaller, so we make our exponent 1 place bigger. And then I go ahead through and make sure my units cancel. And I'm left with kilometers squared. And that's what I'm trying to convert to. Sorry, that's supposed to be a squared, but we're struggling here. Oh my goodness. Kilometers squared. There's my answer. Okay. And then you do the same thing if you're going from English to metric. So for example, this next one, 800. Now again, there's no decimal point. So how many sig figs does that one have? It's only got 1 sig fig. Inches cubed. And I'm just going from inches to centimeters. I guess this isn't going to be a really big bridge because we have a conversion from inches to centimeters. All right, so 1 inch is 2.54 centimeters. But again, whatever you do to the conversion factor, you have to do that same mathematical function to the conversion. Whatever you do to the units, you have to do that same mathematical function to the conversion factor. So then you end up with your calculator spits out 13110. which is a great number. However, that does not have the correct number of sig figs. So again, we're going back here to our original sig figs. The 800 only has one sig fig, so my final answer is only allowed to have one. 10000. And a good rule of thumb is if the number is bigger than 1,000 or smaller than the thousandths place, you should put it in scientific notation. So I'm going to write this as 1 times 10 to the fourth. Make sure my units cancel and I'm left with centimeters cubed. All right. Complex conversion factors. All right, so we just need to make sure that we have things. When we have units on the top and the bottom, we know how to handle those properly. So 9.8 meters. The mathematical function, so basically what this means is meters per second squared. So we're going from meters per second squared to miles per hour squared. So the meters is getting converted to miles, the second squared is getting converted to hour squared. When we, just like I wrote up here, we don't want to put meters per second squared all in the top. Per means, oops, sorry. Per means in the bottom, in the denominator. Per is the mathematical function of division, so you need to make sure you put it in the bottom. The rules, however, are the same. Things that are diagonal will cancel out, so I'm going to use my conversion factor. You could go down to centimeters and inches and then inches to feet and feet to miles, but I do remember my conversion factor for miles and kilometers. So I'm going to go ahead and go from meters to kilometers and then kilometers to miles because that's a little shorter than going the long way, but you should still get the same answer regardless. And then in order to get seconds squared to cancel out, I have to have seconds squared here on the top. And then I convert it to hours squared. You could go to minutes and then to seconds if you wanted, or seconds to minutes and minutes to hours. 1 kilometer is 10 to the third meters. 1 mile is 1.61 kilometers. And then I'm going to do what we just talked about on the last slide. 1 hour is 3,600 seconds, but it's not just 3,600 seconds. It's 3,600 seconds squared, so I have to square this whole conversion factor. Then I multiply across the top, divide by what's in the bottom, and I round to the appropriate number of sig figs. So go ahead and take a second and solve for that. You get a nice big number. I'm only allowed to have 2 sig figs because I always go back to my starting number. So I end up getting 79,000. But again, that number is bigger than 1,000, so I'm going to convert it to proper scientific notation. And then I'm just going to go through and check my meters squared, my meters cancel out, my kilometers cancel out. My miles do not, but my seconds squared cancel out. So I have miles on the top and hours squared on the bottom. Miles per hour squared. So that's my conversion factor. Sorry I have chicken scratch. It's hard to write on this pad. Okay, so you also need to be familiar with trig functions. Not these. Honestly, it's okay if you do know those, but these are the main ones that you need to make sure you're familiar with. We do use trig when we're dealing with Newton's laws and forces, projectile motion, just a lot of things. You have to be familiar with sine, cosine, and tangent in order to solve for them properly. So let's go ahead and solve a problem using some trig functions that says a plane is flying due north at 150 meters per second. There's a crosswind blowing at 15 meters per second east. What's the final speed and angle measured from due north that the plane will fly? So go ahead and draw yourself pictures. The best way to do physics is to draw pictures. So I have a plane that's flying. That's terrible. So sorry. A plane that's flying. That's not much better, but due north. So we know what direction north is at 150 meters per second. And then we have, and this is a very applicable problem because this happens all the time. Obviously, we have a world where planes fly around and winds blowing. And then I have a eastward wind that is 15 meters per second. So since this isn't really going to help us find what direction The plane is flying. We do something called tip to tail when we're drawing vectors. These are called vectors. They're arrows used to represent the direction that things are going. So tip to tail just basically means if I have two vectors like this, I draw one terribly squiggly line, meters per second, and then I draw the next one's tail at the tip of that one. And then if I had more vectors, I would keep continuing them on tip to tail. And then when you're drawing your resultant vector from that, you go from the tail of your initial one to the tip of your final one. And that right there is the resultant vector of those two vectors combined together. So basically they're asking me, what is this value? What is the plane actually doing? Since it's trying to go north at 150 meters per second relative to the ground, but the wind is blowing at 15 meters per second to the east relative to the ground, the plane is not going to end up due north. It's going to end up over here and somewhere in this spot. And we want to know, what is the plane actually doing? How fast is it going because of that eastward wind? And in what direction is it going? So you can see right here we have a right triangle. This is the hypotenuse that we're trying to solve for. And then they are also asking us the angle measured from due north that the plane will fly. So the angle measured from due north. So I want to know, what's this angle right here? So I have two values and you can really do this anyway. I'm going to use Pythagorean theorem, a squared plus b squared equals c squared to figure out, I'm calling this my c value. So 150 squared plus 15. And honestly, you know there's more than one way to solve this. You could solve for theta first using tangent, and then use sine or cosine in order to find c value, or you can do it the way I'm doing it and do Pythagorean theorem. I'm not going to solve for c squared. Just going to solve straight for c. You should end up, once you type this into your calculator, again, I encourage you to be solving for these. Pause the video, solve for them, and make sure you're getting the same answer. So it's not terribly much greater than the normal 150 meters per second, but think about it. 15 meters per second due east compared to 150 is very small. So your hypotenuse is going to be not very large. And then I'm going to go ahead, although you could use whatever, you could use any of the trig functions at this point. I'm going to use tangent just because I have my original two values and I did round that 151. Tangent of theta is opposite over adjacent, so I have 15 over 150. Please make sure, because you may be in a calculus or pre-calc class where you use radians a lot, please make sure you're always in degree mode on your calculator, or when you get to physics, you change it to that, and you end up getting 5.7 degrees. Again, we do expect that to be a small value because our hypotenuse is so large, or so comparably large to the adjacent side to that angle. And then we don't like to just put an angle, because 5.7 degrees is not a degree measured from the normal. Like this direction right here would be where we would normally measure 5.7 degrees. So we are going to be very specific. This is 5.7 degrees east of north. Now they are asking us to put that degree relative to the due north direction, but I still want to be specific enough to say this is 5.7 degrees measured east of the northern direction. So I'm traveling at 100, the plane is traveling at 151 meters per second at an angle of 5.7 degrees east of north, because you could also subtract that from 90 degrees and say it's that much angle north of east. So you have to be very specific with your angles. All right, so I think this is the last thing. Yeah, the last thing that you need to know how to do, and this will pop up multiple times throughout the course of this honors physics, is linearizing data. And I'm going to encourage you right now to go ahead and pop into these two links and then come back to this video, because it's really, really important that you understand what the point of linearizing is and then see somebody linearize some graphs. So basically, there are different, and we talked about this before, and again, please go watch the videos. There are different functions other than linear, right? We have linear functions, but we also have quadratic functions, We also have inverse functions. We also have side opening parabolas. We have top opening parabolas, we have inverse functions, and we have side opening parabolas. These are all really important that you know and understand. And again, they are explaining these in these two videos. So go through the videos. Now, the whole point of when we are linearizing is to take these functions here, all the ones that are not linear, and convert them or learn how to convert them into linear functions. Because when you have a linear function, it has this great little y equals mx plus b equation that is very easy to work with, and it's very easy to solve for m, the slope of a linear function. And then once we solve for m, it usually gives us some piece of information that we're looking for when we're doing physics. So it's a telltale value that can help us in a lot of different aspects of physics. And they give a couple examples in the video, but we're gonna go ahead and again watch the videos first and then come back and try this example. We're going to linearize this data, this set of points. So it's not always given like this, but in this particular example, the x values are here and the y values are here. So almost always time is on the x-axis. I mean, I can't think of any examples off the top of my head right now that time is not on that axis. So your first job is to find out what kind of relationship these two variables have. So we're going to plot the data. If you ever have a question about what's supposed to be plotted on the y and x axis, you can ask, but oftentimes, especially since we have top opening parabola and side opening parabola, it will sort itself out even if you flip them. So just giving you a heads up. We are always given an extra column because we have to take, once we analyze the data and we know what kind of relationship we have to take and manipulate the variables. So I'm going to go ahead and take this data and graph, always labeling my axes, time in seconds and distance in meters. So my time goes from 0 to 5. So I'm just going to skip 1, 2, 3, 4, 5. And then my distance goes from 0 to 125. So again, you can kind of figure this out yourself, but the way I plotted it, every single line is 10, 40, 60, 80, 100, and 120. Now, it's important that you do this well enough that you can see a proper curve. So I'm going to go ahead and plot my points. I have, of course, 0, 0. I have 1 and 5. I have 2 and 20. And you're just doing this, or watching me, but I would encourage you to linearize as much as possible. 3 and 45. And maybe you can even see right now what kind of graph we're starting to get. 4 and 80, and 5 and 125. All right, so hopefully you're seeing as I'm doing this. I'm terrible drawing a straight line, so heavens knows what this is going to look like, but here we go. And not too bad. Obviously, you wanted to go through the points. I can't erase at this stage, so we're just going to, because I haven't figured out how to do that. But you can see that this is quadratic. Okay, this is a parabola. So it's quadratic. Just making a note for myself so I know. Remember that a quadratic formula looks like this. Y equals x squared. Okay, now that's really generic. It's actually y equals mx squared plus b. So you can have other values in there and it can even get more complicated than that. But what I see is going on right here is that my y is going to stay the same. So I'm actually going to keep this whole column and graph it again. Okay, I'm going to keep the y values the same. So I'm just going to go ahead and do that right now. Distance in meters. I don't want to do that. Sorry, guys. I went ahead and got out of that and didn't mean to. Distance in meters. However, my x value needs to be squared. So my third column over here, I'm going to do x squared. And what that means is the time is going to need to be squared, so my unit is second squared. So of course 0, so I take my entire x column and I square everything. 0 squared is 0, 1 squared is 1, 2 squared is 4, 9, 16, and 25. And then I graph these two columns. So instead of graphing this, because I already did that to figure stuff out, I'm going to graph distance on my y-axis, and I'm going to graph on my x-axis. Now is going to be time squared. And it has units of seconds squared. All right, so I'm going from 0 to 25, so I'm going to do, I guess, just, I suppose, similar to what I did before, but multiples of 5. So 5, 10, 15, 20, and 25. All right, now what we expect to have when we linearize, when we adjust our data based on what we concluded we have as a relationship, I'm going to expect a straight line. So I'm going to put in my point 0, 0 is my first point. When I have a time of 1 second, it is a distance of 5. So it's going to be a little crammed here at the beginning. So I have 1 second. Oh, I didn't put my distances on here. They're the same, 20, 40, 60, 80, 100, 120. All right, so I have a distance of 5 meters and a time of 1 second. So 1 second, 5 meters. So my next point is really close here. And then I have a distance of 20 meters at a time of 4 seconds. And then I have a distance of 45 meters, time of 9 seconds. And you can see now this is looking linear. This is not looking quadratic anymore. We have a distance of 80 meters at a time of 16 seconds. And a distance of 125 meters at a time of 25 seconds. So your points get a little spread out as you go, but look how perfect that linear function. It is no longer quadratic. It's no longer a parabola. It's a perfectly, see if I can draw this perfectly straight line, linear function. Okay, now what we know about linear functions is y equals mx plus b. However, we adjusted. It's no longer y equals mx plus b. It's y equals mx squared plus b. Now, my b function is 0 because I have my y-intercept at 0. So basically, my equation of my line is going to be y equals the slope of this line, x squared. So let's find the slope of the line. I'll do the slope up here. Slope is change in y over change in x. So I'm just going to take my first and last points just to make it easy. So I have 125 minus 0 all over 25 minus 0. And that gives me a slope of 5. Now my units for my slope, my units for change in y are meters. The units for change in x are seconds squared. So my slope is actually 5 meters per second squared. It's important that you put those units because if I ask for what's the slope of the line that's linearized, you want to make sure that you have units. So this is the slope that goes in for m. And then the last thing that I do expect you to do is actually put this in terms of variables. So instead of leaving it as y equals 5x squared, what's my y? Well, my y is distance. You can put a capital D or a lowercase d, whatever you want. And then I know my slope is 5. And then my x value is t squared. So this is the equation of the line. This is my ultimate goal right here. This is the equation, and this is actually the equation of this line. And it was, we used this information right here to give us the equation of that quadratic formula. Well, that is the quadratic formula. I hope that makes sense. That looks like complete chicken scratch. It would be a lot neater if I wasn't writing on the screen, but I encourage you to go and do some of the couple examples. I think there's an example or two of linearizing in the, maybe only one example, but you can definitely find even more examples online for linearizing. You will need to linearize just now. That's why we're learning it, but you'll need to linearize in future chapters. when we're figuring out different data. Okay, hopefully that helps. Go ahead and do your example problems, and I encourage you to check along the way using the key that you can find online in Schoology.